Okay, so this is going to be a quick demo of creating a problem from scratch, and we're going to see how things go. I'm actually going to start off by replicating something I did with my Section 513 class. I think it went really well, and it ended up being a pretty interesting start to a problem. So I'll just basically show you that, and then I'll finish off the problem. Okay, so for our little mini SIP problem creation project, I'm expecting that you'll be making kind of a two-part or three-part problem. So that's going to involve something geometric, right? You'll be required to use some sort of volume formula, an area formula of some type, pick some 3D shapes or 2D shapes to work with, and come up with a real world scenario where you can combine everything together in an interesting and creative way. So one student recommended that we take a cylinder and put it on top of a half cylinder. So we'll see what that looks like. So this would be a cylinder here, and that is going to be like this, and then that's going to be sitting on top of a half cylinder, which looks like this. So this is kind of the sculpture, I guess, that we're looking at, if you want to think of it that way. It's this interesting thing, and it's a three-dimensional figure. It's a half of a cylinder with a full cylinder sitting on top of it, okay? So we can imagine that they're just barely touching. And so then there's actually no part of the area of this cylinder is actually being blocked by this cylinder. It's just kind of barely just touching. So we're not really covering up any area. Okay, so the whole area of the cylinder and the half cylinder is showing. And it's also important to note that the bottom of this half cylinder is a rectangle. That's what the whole sculpture or structure is sitting on. So the surface area, if we were to think about it, is made up of the bases of the cylinder, the half bases of the half cylinder, the bottom part of that bottom cylinder, the rectangle, and then also the kind of curved facade, the curved sides of the cylinder and of the bottom half cylinder. Okay, so that's the surface area. The volume is just the entire volume of it. And actually what we're looking at here is we're looking at 1.5 cylinders. So the volume of this structure is 1.5 times the volume of just one cylinder, right? Assuming that the radius of this guy is the same as the radius of this fella here. Okay, so the radius here is the same. Good. All right, this is just thinking about what we're looking at. And this was our choice, right? We decided we wanted to make a shape that looks like this. We can do that. This is a composite solid. That's what we can call this. It's a composite solid, which means that it's composed of multiple solids. That is a cylinder and a half cylinder. Okay, we're just talking. Now, what we'd like to do is to introduce some sort of problem. And to do that, we need to give information and we need to ask for information. Okay. So what we could do is we can say, okay, well, maybe I'll decide to give you the numerical value of the surface area of this 3D object. Okay, I'll give you the numerical value of the surface area, and then we can try and find out what the volume is going to be. That could be interesting. So let's say I give you the surface area of this figure to be 3,000 square meters. Okay, great. Surface area is, 3,000 square meters. And the goal is to figure out what the volume is. Okay, so for every problem, there's going to be a goal and there's going to be a starting condition, information that's given. Okay, well, sometimes when you make a decision like this, you will have made a good decision. And in fact, it will be possible to solve the problem. Just with the surface area, it's possible we'll be able to find the volume. But you need to be aware that when you create a problem from scratch, sometimes you're unable to go from the starting conditions to the final result that you want. So as you try and solve it yourself in this preliminary stage, you're going to maybe come up against some kind of stopping point. Some point you get stuck. And that's okay. It doesn't mean you've done anything wrong. It means you need to adjust the information that's given so that it can be a solvable problem. Okay. So for the project, if you give me a problem that is not solvable, well, first of all, you won't be able to solve it either, and that's part marks for that's part of the grade, your ability to solve it. But if you somehow mess up and you solve it by accident and it's in fact not solvable, you're probably going to fail. Okay. So to pass this, you need to have an actual solvable problem, which takes some trial and error. So let's see what happens. Our idea is to give the surface area and find the volume. Okay, so let's start off then by taking the surface area number 3000, and then we'll just equate that with the formula to find the surface area of this composite solid. Okay, we want to find the surface area. Well, we know the surface area, so we want to basically express the surface area in terms of some equation, right? Some variables. Okay. So what's the surface of this solid? Let's start off maybe just generally. We could see that the surface of this solid is made up of the lateral areas and then the bases. Okay, we'll start with the bases. So here we go. We've got this here, which is one base of this composite solid, or it's the mixture of the base of the cylinder and the half cylinder. And also over here, we've got the base on the other side. So we know our surface area here is going to be the area of the bases plus the lateral area, which is everything else. And so we know that the area of the bases is going to be, well, it's two circles, right? It's going to be two circles. So 2 times pi r squared. Plus, there's also two half circles. So plus 2 times pi r squared over 2. Right? This is the half circle, so it's the area of a circle over 2. And then there's also 2 of those half circles. So we have 2 pi r squared plus 2 pi r squared over 2. Great. That's the area of the bases. This is the orange part of the area. And we can simplify that too, and we're going to do that. All right. Now we need to take a look at the lateral area. So the lateral area is everything else. It's the whole surrounding of the shape, right? Which includes the top part, the bottom part. And remember that little rectangle at the bottom too, the pedestal that it's standing on is also part of that surface area. So we need to be able to visualize here what the surface of our object is. So the lateral area is going to be a little bit more challenging, which is okay. But remember, we also have access to formulas in our Math 3000. We can Google these things. And so the lateral area for a cylinder, so talking about just the top cylinder right now, the red wraparound of that cylinder, that's going to be the perimeter of its base. So the perimeter of the circle, because this is the base. The perimeter of a circle is the circumference, 2 pi r. So it's going to be the perimeter of the base times the height, right? So then this whole structure, it has a height, or in this case, since it's flat, it has sort of this length. But we'll think about it as like the height of the cylinder. So it's going to be the perimeter of the base of that top cylinder times its height. That's going to be the top surface area, which, if we want to be more specific, is going to be 2 pi r. That's the circumference times height. Okay. So again, if you need to rewind, you can do that. But that is the lateral area for the top cylinder. But that means that we actually have to find also the lateral area of the bottom cylinder, right? That makes up the whole lateral area of the entire composite solid. So we know that 2 pi rh here is the total lateral area for the top cylinder. So that means that the bottom cylinder, since we cut it in half, is going to have half of that. So we're probably going to want to add on 2 pi rh over 2. So half of the surface area of that top cylinder. And last but not least, we're just missing that bottom rectangle here, which is what the whole thing is sitting on, right? That's kind of like the inside of the cylinder that was cut in half. So we need to account for that. And that's a rectangle, which is r by h. That's the length times width. So rh. Good. RH. Beauty. So this is our whole thing. Let me clean this up a little bit. PB times H was just this. And so we're done. This is our formula for the lateral area of the whole shape and also the area of the bases. Let's just double check and quickly review. So the area of the bases, there's 2 circles and 2 half circles. Actually, if you combine all the bases together, there's actually just 3 full circles, right? This is circle number 1. This is circle number 2. And then circle number 3 is made up of this piece and this piece put together. So we actually have 3 circles, which should be 3 pi r squared, right? And you just get that by simplifying what you had over here. 2 pi r squared plus 2 pi r squared over 2. Well, these folks cancel. So 2 pi r squared plus pi r squared is 3 pi r squared. Great. That's the area of the bases. Then the lateral area is 2 pi rh plus 2 pi rh over 2 plus rh. So 2 pi rh over 2, we're going to cancel the 2's out. That will simplify it. And we get 2 pi rh plus pi rh plus rh. Great. If this feels complicated, good. Excellent. You're challenging yourself a little bit. This is really nice. Okay. We're still just manipulating familiar things like areas of bases and areas of lateral faces, and that's okay. Now we got to stop for a second, because we have an equation that relates the numerical value of surface area to the kind of algebraic part that would allow us to find the surface area, right? This whole thing. Well, how many variables do we have right now? It's an important question to ask. How many variables do we have? Well, we've got r, and we've also got h. So this poses a bit of a problem. It's a sticking point. If we have one equation, then we can only use that equation to solve for one variable. This is where things get really exciting. If you recognize now that the surface area was not enough information for you to find the volume, that's okay. You just need to introduce now either the specific measurement of one of these things, right? If you tell me what the radius is, 5 meters, let's say, boom, easy. That means that I can then go ahead and replace the radius with that number, which reduces this just to a 1 variable equation, right? R would no longer be a variable, it would be a number, and then you would just have good old h, the little pink h here to solve for. Now that's a bit easy, okay? That's kind of the easy way out, is just by, oh, well, I guess I'll just give the number for one of them. To me, a more interesting thing to do here is to introduce a second equation that relates the 2 variables you have. For example, we could make the equation, say, for example, r is equal to 2h. Or we could say equally that h is equal to 3r. What we're doing here is we're actually just making a relationship between height and radius. We're saying that they're related. The measurements aren't independent, but actually, maybe in this case, we could say that the height is 3 times the size of the radius. Maybe those are the specifications of what we wanted our sculpture to be. We want it to be longer than it is wide. Great, you're the one making the problem, so you choose. So let's stick with this. We'll say that h equals 3r. This will be our new equation that we add in here. This is going to be added, which means it'll have to be available from the beginning of the problem, right? From the outset, we'll say not only is the surface area 3,000 meters squared, but we're also going to tell our problem solvers that we have h equals 3r. Okay, good. So now this is part of our initial condition. We give 2 pieces of information, that the surface area is 3,000 meters squared, and that the height is equal to 3 times the radius. Beauty. Cool. So now we're going to continue, because we have 2 equations, h equals 3r and 3,000 equals all of this beautiful stuff. So if we have h equals 3r, this means that we can recall back from like chapter 1, we can do substitution method. So wherever we have an h, we can just replace that by 3r, because they're equal to each other, right? This is the substitution method. So we're going to use this to say that 3,000 is equal to 3 pi r squared plus 2 pi r, and the h now, well, that's just going to be 3r. And then we're going to go pi plus pi r h. But again, h is going to be 3r plus rh, but h is going to be 3r. And now that's our whole equation. The beauty is that we now have everything in terms of r. R, 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 R. R. Merry Christmas. Okay, so 3,000 equals a whole bunch of stuff with r. Now we just got to simplify the right side, and we could actually solve for the radius. This is what we're realizing we can do. After all this work with the surface area and this new little mini h plus 3r equation, we now know that we could solve for the radius. And if we find the radius, well, that should allow us then to find the volume. For two reasons. One, the volume is going to be based off of the radius, but the volume is also going to be based off of the height, which itself is equal to 3 times the radius. So we basically made the radius the key to unlocking the whole problem. Wow, amazing. That's math in action for you. So it should make logical sense what we're doing here. We're going to continue, and we're going to simplify the right side of the equation. Now we're basically done with the preparatory phase of this part of the problem. We know that we're on the right track. One equation, one variable. So you can maybe fast forward through this part if you aren't as interested in watching the actual simplification. And then maybe in a minute or so, we'll be done simplifying, and then we will solve for r. Okay, so 3,000 is equal to 3 pi r squared plus, let's see if we can simplify what's going on in the brackets here. We have 2 pi r times 3r. So 2 pi r times 3r. Well, the r's are going to multiply to give r squared, and the 2 times 3 is going to multiply to give 6. So that's actually going to be 6 pi r squared. Okay. Then we're going to go to the next term, pi r times 3r. Well, here again, the r's are going to multiply. So we're going to get r squared. And then it's just a 3 and a pi. So it should be 3 pi r squared. And last but not least, we have r times 3r, which is r times r is r squared with a 3. So 3r squared. Beautiful. That's a lot simpler. So now we have 1, 2, 3, 4 terms that all have r squared in them. So these are all like terms, and they can just be added together. So 3,000 is equal to 3 pi r squared plus 6 pi r squared plus 3 pi r squared plus 3. So you'll notice here what I just did is I basically added up all the coefficients. All the numbers multiplying r squared, they're going to add up, and that's going to be how many r squareds we have. 3 pi r squareds plus 6 pi r squareds, etc., is going to be some number of r squareds. So 3,000 is equal to, let's put in our calculator, 3 plus 6 plus 3 is 12. So that's how many pi's we have, times pi is 37.7, plus 3 is 40.7. So we have 40.7 r squared, right? It's actually 40.699, but that's pretty darn close. So let's keep going. 3,000 is equal to 40.7 r squared divided by 40.7. And that is equal to 73.71. That's r squared. Okay, remember 40.7 is going to cancel. Then we can square root both sides, and 8.59 is equal to r. Beauty. We got r. Let's try and show everything here. Great. So r is 8.59. Beauty. Now, we found r, so automatically right away we're going to want to see what else we can figure out. And remember our good friend, h equals 3r. Okay, well that's good. That means if r is 8.59, h is equal to 3 times r, which means h is equal to 3 times 8.59, which means h is equal to 25.5. 0.76 approximately. This is meters for both. All right. What a treat. Look at us go. We now have the radius and the height, which means we have everything. We are the gods of this problem now that we created from scratch. Woo! We have the radius, we have the height. That means we can now start translating this into volume. Okay. So the volume of this object is, well, this is going to be easier than the whole surface area thing, actually. Volume is much easier. Volume of a prism, which is what cylinders are, is just area of base times height. So volume is equal to area of base times height. Now, if we imagine the sculpture as a single kind of funky looking prism, it's just a mixture of a cylinder and a half cylinder. The combined base of it is 1.5 circles. And then the height is just the height. So if you want to think about this really succinctly, really compact, then essentially what we have is we have this integrated shape here, which is our base. And then that has a height, right? So this whole thing here is our base. So if we find the area of that base, we can multiply by the height, and we've got the volume. That's pretty nice. So let's basically turn that into an equation. Area of the base is the area of 1.5 circles, right? It's just 1.5 circles. So that's basically 1.5 pi r squared. And we're going to multiply that times the height, which is equal to, as we know from here, 25.76. So let us combine the volume equals 1.5 pi r squared times 25.76. We know what the radius is. The radius is 8.59 squared times 25.76. Pull out those calculators, folks. 8.59 squared times pi times 1.5 times 25.76 equals 8,957.22 meters cubed. And we are done. Part A of our situational problem is finito. Let's zoom out and take a look at all this glory. Oh my goodness, that's beautiful. This is the whole thing, the whole shebang, the whole 9 yards, the whole kit and caboodle. Man, that's fun. So how long did that take? I don't know, maybe 20-ish minutes, 25 minutes. Okay, good. Well, that's half of your sit prop time, approximately, maybe a little bit less. And so we can move now into phase 2, which is, okay, I want a second part of this problem. Now that I found the volume from the surface area and our little h equals 3r, let's do one more thing just to kind of round off the problem. And it'll build off of what we got from this result. So we know what the volume is. Let's do something with volume, and maybe, since we learned about equivalence, we can do something with equivalent volume. So equivalent solids. That would be nice. Kind of a logical place to go from here. So this is a volume, and we're going to do something to do with equivalence. So I don't know. I mean, we could take this volume and we can say, okay, well, I built this sculpture out of brass, or I built it out of some sort of metal, maybe solid gold, actually. Okay, I built this funky sculpture out of solid gold, and I want to actually, I'm getting sick of it. I want to melt it down, and I want to turn it into a large pyramid, or I want to turn it into just this large sphere, maybe. That could be fun. So I want to make a sphere by melt a giant sphere of gold put outside of my house on my front lawn by melting down this sculpture. Sounds great. What I want to know is, what's going to be the radius of that sphere? Boom. Part 2 of the question. That's what I want to know. What is going to be the radius of a sphere if it has the same volume? The volume of the sphere is equal to the volume of this original structure. Boom, this is part B. what is the radius of the sphere if the volume of the sphere is equal to the volume of the structure? Boom, equivalence, you're in business. This is actually pretty straightforward. We're almost done. So part B is going to be way quicker than part A. Part A was the tricky part. Let's finish it off, folks. We know that we want to know the radius, and we need to say that the volume of the sphere is the volume of the structure. So great. We know what the volume of the sphere is then. The volume of the sphere is equal to 8957.22 meters cubed because of the equivalence, right? Good. So the volume of the sphere is this. And the volume of the sphere, the formula for the volume of a sphere is 4 pi r cubed over 3. So we just got to solve this equation now, right? We only have one variable. Our variable is r. So let's just go ahead and solve it. And we'll be done. Amazing. Look at that. Zip prob. This will take us less than 2 minutes. So we're going to multiply both sides by 3, right? We're trying to isolate r. So we'll multiply both sides by 3. 4 pi r cubed is equal to 8957.22 times 3 is 26,871.66. We'll divide by 4. Or I think in class we saw this. We multiplied 4 and pi. So let's do that. 4 times pi is 12.56 or 57. 12.57 r cubed is equal to this number, 26871.66. Divide by 12.57. Divide by 12.57. And that's, hold on a second, 26871.66 divided by 12.57 is 2,137.76. That's r cubed. And then we can cube root it. So the cube root is 12.88 meters. Woo! Nice. We'll do purple. Cool. So we know what the radius is then. If we melt down our sculpture, turn it into a giant sphere, it's going to have a radius of 12.88. Nice. And we're done. That's great. That's the whole sit prob. That is the whole... Oh, that's a wonky smiley face. Looks like a winky face, maybe. Okay. Great. We're finished. That's the situational problem. Let's take a look at it. It's beautiful. It's gorgeous. We picked a figure, a 3D shape to start with. We gave a surface area. We gave a relationship between height and radius without giving the numbers. We just said they were related to each other. And then we did a whole bunch of calculations to figure out what the radius was. We transformed that into the height. We then decided that, we use that to find the volume. And then we decided we wanted to do a part 2, which uses the volume. So equivalence was a natural step from there. We said, okay, let's say I melt this thing down, make it into a sphere. It'll have the same volume of gold. I'm not losing anything, but it's going to change shape. And so I basically make an equation for the volume of a sphere, knowing that it's the same as the volume that we got before. And then we solve. We get the radius, and we're done. Happy campers. 100%. So that's it. Again, if you have any more questions about this, I'm going to have a veil on Wednesday, day 3. And also, if you're not available then, just let me know. Shoot me an email, and we will talk and set up a time to meet as well outside of the regular avail hours if you need. And with that, have a great rest of your weekend or week whenever you're watching this. Stay hydrated, stay safe. Math is always watching over you, and so you are safe if math is around. Have a great one.